Yep. Okay. Okay. Thank you everyone. We come back from the break. Right. So, so I believe that all you have learned a lot of things, right, about the things we discussed just now. A lot of things have been learned. So I think it's good for us to recall back what we learned. What you understand, what you it's important to recall back, right? So that we can know how much you understand the lesson we learned so far, right? Maybe I ask Della, what is your what have you learned so far from the first lesson?
Okay, so from the first lesson, like the basic concept of how diode is supposed to be more suitable to be used as a voltage source is important. And
That's good.
there's also the fact that when it comes to the usage of like transistor devices, the saturation region is much more important to be used for analog devices, whereas for digital application it will be more suitable to be used in the triode region. And even for the RC concern, like for example, if you want to lengthen the time of it reaching the output that you want, then you have to manipulate the RC constant. How do you manipulate the RC constant? Is either you change the value of R and C. And also, meanwhile, for the low pass filter, I learned that for each and every pole, it will contribute a maximum of 90-degree phase shift, and at the cutoff frequency, each pole will contribute like about 45 degree phase shift, which is standardized. Yeah, this is what I learned so far.
Okay, I think you already covered everything. Maybe anything to add or mention anything, one point in it?
So just maybe a little bit of things like, so for the RC constant, so actually what the thing that we talk about, for example, is it RC1, RC2 constant? That one
RC3,
one RC2, RC. That one actually correlates to the percentage of the output that you want. So for example, one RC actually tells you about it's reaching about 68% of the
63%.
63% of the output, and whereas for example 4 RC is almost like 98% of the desired output. There's one more thing to add on.
Yeah, correct. That's good. I think I get how you can get the lesson quite well. Lastly, Jackie, so recall back one thing to learn.
From one interesting thing is that when we have the transistor, right? So in triode region, it is more suitable to be used as digital part, is because it is faster because of the R1 is smaller. So and then for the analog part, we usually want to use for the bigger R1, which is the saturation part, because it is becoming the current source.
Okay. But one thing that to remind all you, okay, one thing that for the inverter that I mentioned here, right? This inverter that I mentioned here, right? Okay, right. Although I say that okay, it operates as a linear and cut off, right? But actually at the center here, right, both actually is turned on. It's still the path that in saturation when you're applying the paths, right? Okay, like although I say that okay, it's a for digital logic bias in either is cut off or linear triode region. The one applicable when you put a DC voltage, right? Example, put a 0 volt here. Put this one turn on, this one turn off. This one linear, this one is cut off region. Yeah, it's true. But for application that when you have a pulse, right? You have a pulse switching. Basically at the center here, basically you have the path. Actually when you apply 0 and 1 here, 0 volt here, actually there's no DC current flow at all. This is the advantage of CMOS transistor, right? Where you can turn off the DC current, right? Where with the old technology you have this one, resistor, remember resistor, and this one. Basically we cannot turn on the high side. That's why it's always a DC current flow before the invention of the CMOS technology, right? This CMOS technology helps us that when you apply the DC, right, it can totally cut off the current. We only consume current when there's a current flow from VDD to ground, right? When you apply 0, basically this one on and off. There's no DC current flow from VCC to ground. But where in the application they have a clock signal or the switching signal, actually they still involve three operation regions. Example, here is here is a linear, here is a cutoff, and at this point, basically both are turned on. Both are at the center. Let's say VD over 2 here. Basically, both transistor PMOS and MOS are turning on, right? Where actually the direct current path. That's why normally you plot the VD current, you see this kind of behavior. The VD current, you see this kind of behavior. Sudden up and down. This is called peak current, no? Peak current, right? And here actually is 0 current. This is where your transistor operate in the cut-off region, right? But that's why we call it switching current, we call it dynamic current. Actually, all this current at the end will convert to become the RMS current, right? RMS current is a DC current in AC viewpoint, right? So all this is switching current thing. Although we say that CMOS doesn't consume DC current, right? This is the first thing. But in actual world, when switching actually contribute to the what we call RMS current, right? Remember the RMS current, right? You take the peak voltage, peak current divided by square root 2, right? So you get the RMS current, right? Okay. Example in oscillator also is kind of switching current, right? Actually contribute by that, right? So I try to give you an overview like how important the R-ons, okay? But in this part, it still depends on R-on also. So you have to get the right time for that. But at a particular moment at the center here is saturation, right? But there's some time here, linear region it depends on your R-on of your circuit like inverter here. That's why I told you this is R-on, right? But increase the size, we still reduce R-on. So your RC constant reduce, so your charging will be faster, right? Let's say we look at this point, this is R-on. So on turn on, you have R-on and you charge it, this point will pull up. You pull up, after that, this guy turn on, you pull, turn on, turn off, you pull down. How fast you pull down depends on R-on. R-on dependent on the size of the switch, right? So it basically tell us about the important R-on, important application. If you want to do analog signal, most likely you can need to biotransient saturation, right? You do digital signal, you must consider the triode region, or biotransient triode region, right? So this is a key concept that I tell you. Maybe I can just quickly go through. Okay. Like I mentioned, the unit our cost outline, I mentioned to you before that, but I just recall back the thing we're going to study, right? In this course, we cover about the current mirror, the fundamental example I mentioned, what is voltage source, what is current source, right? And what is the single stage amplifier, what is the two-stage amplifier for the cascade amplifier, how to do a frequency compensation for your negative feedback loop, right? So all actually will cover our outline, course outline here, right? So a quick callback, I think important callback, right? I told you, in this world, everything is a linear device, right? Example is the resistor, capacitor, and also inductor. Those that are not linear device is the BJT, MOSFET. If you look at the IDS versus VGS, right, for MOSFET, basically it's quadratic, right? So it's not a linear device, right? So it's an important thing. And also we learn about the sound, we learn about what is voltage source and current source. In fact, these two terms, you will become an analog designer, you must differentiate these two terms very, very well. You know? What is voltage source and what is current source, right? As I mentioned yesterday, voltage source is a battery, right? Battery means that the voltage remains constant when you power up the device, right? You can draw from your supply 1 milliampere, 2 milliampere, but the voltage never drop. This is what we call a voltage source, right? What is example current source? Like I mentioned also, example like when you buy a transistor in MOSFET in saturation region, that one basically is a current source, right? You look at the thing here, right? Your bias here, this is IDS versus VDS, no? Start from here, current almost constant. That's why I call current source, right? Current source important because in analog circuit, if you do analog circuit, there's a lot of current mirror, right? I think that's how we do the how to create current mirror. There's so many, right? No? Actually, all these are current source, you know. So analog circuit, that you must really differentiate what is current source and what is the voltage source, right? If you cannot differentiate well, you know, you have trouble to design the analog circuit, right? So basically, I mentioned to all you also, current source basically it has a very high impedance. Oh, if you have very high impedance, this is a must have. You look at the curve here. You take the R equal to delta VDS versus delta IDS. Where this one are pushing 0, actually you have an infinite impedance, right? That's why we call it a current source. This must have, right? But particularly if you should know this, it will be exactly flat. There's some going up. That's why in real actual device for the MOSFET, they still have some R. R normally is in saturation will be in like a few hundred kilo ohm to mega ohm, depending on your process. Right, it's very high. So as I mentioned, like if you want to high gain, you need a high output impedance, right? So you need to buy a transistor in saturation region. This is a key thing, right? And also I cover about I think this I cover. Example like I mentioned earlier. Normally the first question I ask candidate interviewer, I ask diode. Is diode a voltage source or current source? You know? Basically diode is a voltage source. It's not a current source because you see, if it turns on at 0.7, at 0.7, even current increase, the voltage still remains the same, right? And this actually exhibit the behavior of the voltage source for the diode. Oh, this is a key thing I want to know, right? And as I mentioned, RC constant, right? RC constant is very critical, especially if you are a designer, especially if you do the post-loss simulations, right? Your R and C will affect your rise time, fall time, and also the operation delay, right? So how to control it? That's why I told you that there's an RC constant, you know, like when you reach 1 RC, is your output will be equivalent to 63.2%. Let's say you have 1 volt input, you provide. I think we do a simulation yesterday. You do a simulation, then you have an RC. You put a pulse here, 1 step pulse, right? Your output will rise up. Let's say this is 1 volt. Your output will rise up and reach 1 volt here. But at here, at 1 RC, your output here will be about 0.63 volt, right? At 1 RC, about 0.63 volt. Let's say your step here, putting this is very fast, maybe 1 nanosecond, very fast, right? You put a step to input. This is how you simulate RC constant. I think we do a simulation, right? For RC constant in LT price, we do it. We saw it exactly at 1 RC. We calculate R and C. You put here, alright? Calculate at 1 RC exactly. You get 0.63 volt, right? So this curve also tells us that to reach 1 volt, you need at least, like this is 4 tau is about this 1 RC, 1 tau, 1 RC, 2 RC, 3 RC, 4 RC, and 5 RC. To reach about 5 RC, only you can get the almost full swing to 1 volt here, right? This is tell us that okay, if you want a faster rising time, what we should control?
You must reduce either your R and C.
Yes, correct. Alright. It's no way. Let's say your design for high speed application, you know. No way you can design something high speed if your R and C is very high. very high C, right? To reach that is very, very difficult, right? So that's why sometimes bounded by process also, right? So all this you must take into consideration for your RC constant here, right? Okay. And then after that we talk about the RC filter, right? This RC filter. Actually, this RC filter is okay. It's something we use all the time for analog IC designer. RC filter, it can filter the signal. First function, it filter the signal. It pass through the low frequency and block the high frequency. And what is the second function of low pass filter? Anyone can answer? What is the second function of low pass filter? The sound is good. The first function is good, right? It's good because it is how you filter out the noise, right? It pass the low frequency signal and filter out the high frequency noise, right? Low pass is a good thing, right?
Oh.
What is the second function? Actually, not good thing.
Introduce a pole.
Yes, correct. So introduce a pole, right? So what is the bad thing about the pole?
Contribute to phase shift.
Okay, consider phase shift. So what is bad thing about the phase shift?
Delay.
Delay. That's all?
Oscillation.
Yes, correct. That's why you learn something and link together, right? A pole actually, RC actually, why is bad? Because it contribute a pole, right? Okay, a pole, it contribute phase shift. So when a phase shift of 360 degree, will cause oscillations. It's called Bargusian theorem, right? That's why in the negative feedback loop, all us very worried about the phase shift. Okay, once in your phase shift, you are prone to go to the oscillation region, where it's very bad circuit. Because in negative feedback, we don't want to see oscillation. We are not a design oscillator, right? So all this, that's why very important to say, like some you tell me, okay, one pole control maximum 90 degree phase shift. So in a negative feedback loop, we need to budget how many poles that we can afford to have, so that your phase shift don't reach 360 degree, will cause oscillation. You need to budget that, right? And also you learn about at 45 degree at cut frequency, there's a 45 degree phase shift, right? And maximum is 90 degree, right? So all these informations actually we need it as an analog designer to design a negative feedback system. Very, very important for us. Now we look at here. Look at this formula. Look at this formula. So how we can get the SRC here? Let's get this is a voltage divider. Impedance across the capacitor is 1 over SC. Total is the denominator is the total impedance 1 over SC plus C, and this is 1 over SC. So we get the 1 over 1 plus SRC. So 1 plus is a normal term we use. 1 plus SRC. Easy to remember, right? I always used to remember SRC. What SRC? Right? Remember this is called one pole. SRC. Oh, remember 1 plus SRC. Right? Actually, S is your variable frequency. S equal to
J omega.
J omega. So RC is a constant. Right? RC constant defined by your R and C in your circuit. So S actually is your variable. Right? So this one will tell you that at this frequency, is it can filter out by this RC or not? Okay? S is variable. So that's why normally we do you do the 1 plus SRC equal to 0. Right? From there you can find out what is your S. S equal to 1 over RC. So negative, when you have negative, that means stable. That means stable. You have negative here. Right? So this one define your S here. Right? So define your cutoff frequency. So you want to define cutoff frequency. That's why we have we have this one. Right? So now you look at here. How we get this one? S equal to J omega RC, right? Then can we do more on this formula? This is in the Laplace domain, right? You know? Now I want to ask, I want to try to give all you a quiz. Normally, you find a curve frequency. At which point you find a curve frequency?
Negative 3 dB.
This is a gain. This is a frequency. You always minus 3 dB, right? Always minus 3 dB, correct? Now the quiz is why minus 3 dB?
It's the point whereby if you go beyond that point, you will have more phase shift.
Yes, correct. But before that, why people say minus 3 dB? Why not minus 4? Why not minus 5?
When you extend out the minus 3 dB, it becomes 0. Because this one is in logarithm.
But before that, how we know it's a minus 3?
Is it about the root 2, the square root 2?
Square root 2. Yeah, something related to that.
Because I remember there's something divided by square root 2, like before it converts to gain or something.
Yes. That's why fundamental important. So I think if you learn this right, important you must know. Because a lot of time in simulation we just take the minus 3 dB, right? But as an knowledge designer, you know where this minus 3 dB come from.
This is half power, right?
Half power.
Half power.
But why minus 3?
Square root of 2.
So everything coming from this formula. This simple formula actually will tell you why is minus 3 dB. Okay. Actually, you need to do some magic on this formula, right? A little bit. Then you can get the minus 3 dB. Okay, look at this simple formula, right? You have your V out over V in equal to 1 over 1 plus J omega RC, right? So you change a bit, become 1. This J omega refer to your input frequency of a filter, right? So you change a bit here, become 1 plus J omega divided by omega naught. Omega naught actually is equal 1 over RC. Actually I try to put omega naught is equal to 1 over RC. Right? It's like I turn in here. Or actually RC equal to 1 over 8 divided by omega naught. That's what I put here. So actually this one is your cutoff frequency. Then we turn into the frequency. 1 plus J 2 pi F 2 pi F. This is your input frequency. I try to put F. This one 2 pi F naught. Correct? So after that you just put in, it become 1 plus J F divided by F naught. Okay, and this is your transfer function V out divided by V in, right? So now you have your J. You understand this to get this formula. You have a J here, right? Actually, I got to prove that how to get the minus 3 dB, right? So F is your input frequency, right? F naught your cutoff frequency. So what you need to do when you have J to find the value? What you do? You remember about the how to find a magnitude for your complex number? You need to modulus, remember? Right? So what you need to do? You do modulus. So this one become
Square root.
Square root, right?
of 1 square.
1 square, I go to square, and then this one become j, not j anymore. Okay.
Divided by f.
F divided by f naught, right? Correct? Right?
There's a square.
There's a square. There's a square here. Correct. There's a square. Correct. 1 square plus square. Right? Remember? A square plus B square. Remember the mathematics, let's do your university. Right? So now, let's say F calculus your F will equal to F naught, right? So your formula become 1 over
Square root of 1 plus 1.
1 plus 1 plus 1, right? 1 plus 1. So you get,
1 square root 2.
okay, you try to see 1 square root 2 is what? 20 log 1 over square root 2 is how much? You get. You try to calculate and see. Actually, 1 over square root 2 is a 0.707.
Minus 3.01.
Actually, almost minus 3 dB. Right? This is how the minus 3 dB comes from. Right? It's not like people simply put the minus 3 dB. Right? It's because it's a very follow formula. Right? You look at the formula. You can follow me. Right? It's exactly follow formula because of F equal to F naught. And your influence equal to your cutoff frequency F naught, and then you get your gain actually is minus 3 dB. That means at particular cutoff frequency you measure, actually your gain will drop by minus 3 dB. This is the reason why we look into minus 3 dB for cutoff frequency. Interesting, right? Right? Because you learn this way, you make your learning more meaningful. Right? Because sometimes you take minus 3, sometimes, if you don't know the history behind that or theory behind that, you don't feel the learning is interesting, right? Now you know actually where the minus 3 dB come from. It actually coming from a simple equation. If you manipulate a bit, you can get the minus 3 dB. Right? Correct? Right? So you see, a simple RC, you can learn so many things. As I mentioned to you, RC constant is a large signal. Right? I mentioned the sound, the curve here. It's something related to large signal, right? RC constant. So you must able to differentiate, what is the difference between large and small signal, right? And all these filter, right? All these filter, like I mentioned to you, filter got 2 functions. One is a good function, is a filter out the high frequency noise. The second function of the low pass filter, which is not good, is because it functions as a pole. Pole basically causes a phase shift. More phase shift, you're prone to oscillation. 360 degree, when you have a 360 degree phase shift, when the loop gain is too high at that particular point, and then you have the phase shift, you have the oscillations, right? So from that you learn, how you control the pole, how to control a phase shift in our system negative feedback, won't have the oscillations. Got the point? Any questions? Any question to ask? Right. As I conclude here, so you can see that. I mentioned to you. So I can see here. This is a point. This is a break point. This is one. This cutoff frequency actually is 0.707. Where I come from? Exactly come from here. And exactly at the cutoff frequency, a phase shift of 45 degrees, because tangent, arc tangent is 1 or minus 1?